Alright, Brittany, here you go. This is the official limit definition. This is actually really funny because my son was just here last weekend and we went over the exact same thing in his calculus class. He's like, why are we doing this? And he's like, well, this is the actual math reason why we can do, see there's your text in the background. The actual math reason we can do what we do, that we've done all year long at our for limits. So anyway, here's the actual definition. I'll draw a picture and then we'll do an example and kind of see if we can get a feel for it anyway. And then I'll send this to you so you can take a look at it. Here's the definition. It says if epsilon is greater than 0, epsilon is some small number, then there is a delta, another small number, greater than 0, so that if the distance from x to some number c is less than delta, then the distance between f of x and L is less than epsilon. That's like you're asking, what in the world does that mean? Well, here's a picture, and once we draw this picture, you're going to go, oh. Okay, so say we have this, our function right here, and suppose this is c, and this is L, and this is f. This is just my function f. Just like that. Okay, so basically, this is the definition that says the limit of f of x as x approaches c is L. Okay, so in other words, we're saying is x gets closer to c down here, then f of x, my y values are getting closer and closer. We draw it on the graph here, are getting closer and closer to L. Okay, let's try to picture what this is saying. Epsilon is some small number, and I'm going to get some different colors here going. Can't here. Let's see here. So epsilon is some number bigger than 0. So epsilon is this band that goes around L. Because remember, this is the distance between f of x and L is less than epsilon, so that could be plus or minus epsilon. So that's this distance up and down from L. It says there's some delta that exists, so that if I pick an x value somewhere inside, close enough to c, then f of x, the distance between f of x and L will be, f of x will be really close to L over here. So they're basically saying as x gets closer to c, then this is going to be arbitrarily close to f. Oops. Okay, so in other words, pick a tiny number as close as you want to L. Okay, no matter how, 1/1,000,000th of a unit. Okay, then there's some value that I can pick. As long as I'm closer than that, which is delta, to c, I know that f of that value will be within that, will be that close to L. Okay, so it takes a little bit to wrap your mind around that, but that's the actual math definition, and we say it loosely as x gets closer to c, then y gets closer to L. So let's look at a specific problem here. Let me go back to not red here. Let me get it thicker. Okay, so let's look at the example. F of x is 2x plus 3. We want to show that the limit as x approaches 3 of f of x equals 9. Okay, in other words, I want to show if epsilon is bigger than 0, if I pick any tiny number, then there is a delta bigger than 0, so that if the distance between x and 3 is less than that delta, then f of x minus 9 is less than epsilon. So if I pick an x value within super close to 3, then f of x is guaranteed to be that close to 9, which is my limit. Okay, in other words, delta will depend on epsilon. Okay, here we go. So delta is going to depend on epsilon. In other words, we're going to pick an epsilon, arbitrary epsilon. We're going to figure out what delta has to be so that as long as x is close enough to 3, then f of x is going to be that close to 9. Okay, so here we go. And we're going to start here. Okay, so f of x is 2x plus 3 minus 9, and I'll show you all the steps. Has to be less than epsilon. That's where we want to get to. So that's the same as saying this. Okay. And then I'm going to go ahead and do some simplification. So I get negative epsilon less than 2x minus 6 less than epsilon. Now I'm going to factor out a 2 and do x minus 3 and then divide by 2. So I get negative epsilon over 2 x minus 3 less than epsilon over 2. And what this means is that absolute value of x minus 3 is less than epsilon over 2. So, going backwards, look what we're saying. If this is true here, then just go right up the ladder here. That's true. So if the difference, if I pick an x value that's with the difference between x and 3 is within, the difference between x and 3 is less than epsilon over 2, then guaranteed the difference between 2x minus 3 and 9 is less than epsilon. So in other words, the limit as x gets closer to 3 is 9. Okay, so if epsilon is bigger than 0, and if absolute value of x minus 3 is less than epsilon over 2, that's your delta, then guaranteed f of x minus 3, which is your L, is less than epsilon. So we just said, hey, pick as small as you want, as close as you want to get to 3. I'm sorry, this is 9. Oops. As close as you want to 9, that's my limit. Okay. I can find an x that's super close to 3, so that f of x minus 9 is that close to, that f of x is that close to 9. Let me say that again more clearly. As close as you want to 9, epsilon, that's a tiny, tiny number. I can pick an x value so that the difference between f of x and 9 is less than your choice of epsilon, no matter how small epsilon is. That's what a limit is. That's the halfway to the door thing. If you go halfway, right? No matter, every time you go halfway, if I pick any distance from the door, you just keep hopping and you're going to eventually get it past the mark that I put. Well, this epsilon is that mark. I pick that mark. At some point, pick this x. If it gets within there, I know that you're going to get past the door, get past my mark. Okay? So, look at that. Hopefully that helps. And then go from there. You're not going to do a whole lot more with this. The rest of this, dealing with this anymore, is going to be upper division math. Most calculus instructors like to show you this, maybe do a couple examples like I just did here, and then it's kind of like, okay, move on, let's use it. Okay, there you go.